Okay, thanks for being here, everybody. So we're getting close to the end, right? So the new lectures will end at the end of this week. So we have today's lecture, which will be a turbojet example problem. And then we'll do introduction to vapor compression, refrigeration, and heat pumps. So the good news is that that's, it's not review, but it's kind of like a 4-component Rankine cycle, but we run it backwards because its job is the opposite thing, right? So heat engines, we're putting heat in and getting work out. These temperature control devices like refrigerators and heat pumps, we're putting work in and we're controlling the direction the heat is flowing. So it's kind of like running it in reverse. And then we'll do an example with that. So then down here, we have scheduled reviews on Tuesdays and Wednesdays. Now, if people are interested, I would also run review classes next Thursday and Friday, just in our normal lecture time. So do you feel like that's something that you're interested in doing? If anyone's interested in doing that, I will do that. Okay, so we'll do that, and I will have I'll have that set up, right? So we'll do that, and then if we find out that we don't need the time, then we just won't do it. But I mean, at least for now, we'll plan to run review classes on Thursday and Friday during class time. So what are we going to do during those reviews, right? So because at that point, I'll already know what's on the exam. So typically what I do is I get students to look through the textbook and find problems, preferably find difficult problems that are maybe different than something that they'd seen before, so that I can kind of run through the solution method and kind of show you in real time how I would go about solving these problems that I haven't necessarily seen before. I think the problem, so probably it'll be about one problem per lecture, which is why I want to add those extra 2 lectures, right? I think there are basically 5 choices, right? And we only have 4 lectures, so some of them we'll have to not do, right? There's the internal combustion engines, right? So auto or diesel. I think it makes more sense if we're going to do that to do a diesel problem, because it's more difficult than an auto problem. Although most diesel problems are the same, sometimes it's useful to go through these. I know we went through them all pretty quickly. A Rankine cycle that's complicated, so maybe that has regeneration. If you could find one with regeneration and reheat, or even if you could find a picture of one that doesn't nicely fit into some kind of a box, right? That's maybe kind of looks like reheat and regeneration, but it looks a little weird too. If you can find something weird, that's good, right? Because then I can show you how I would go about doing something that maybe we haven't talked about. But if you follow the method that we're talking about, you can still do it. Right, then there's a Brayton cycle. Here, this is the Brayton cycle with all the pieces in it. So sometimes people, it's tricky to do this, particularly drawing the TS diagrams can get pretty tricky, right? So this is a good one. The turbojet, we'll do an example for turbojets today, but if people want to do that again next week, we can do that. And then we'll have vapor compression refrigeration, which, I mean, granted, you'll know more about after tomorrow, right? So I know that we haven't really done that yet. Oh, it looks like there's a message in the chat. Sure, yeah, that's not a problem. So we don't have to decide now, but if maybe next class I'll ask people for what their thoughts are on what's the first, I guess, what cycles we want to cover in the review lectures, and maybe get people to volunteer to bring problems in to class. So that's not something we'll do today. I won't put you on the spot, but tomorrow I'll ask people to kind of divide up the workload here so you can bring in some tricky questions that you can share with me. Okay? So our job for today is to kind of, first we'll go over sort of a brief review of turbojets, and then we'll do a problem, right? So the thing about the turbojet is it's a heat engine, but it's different than all the other heat engines because we're not interested in mechanical power, we're interested in thrust power. And that's why we're not going to ask for an equation for thermal efficiency, right? So even though we presented that in class, We're not going to ask that on the test. To solve these, you kind of have to pretend that you're one of those crazy people that stands on the wings of planes, right? So that it feels like the plane is stationary and the wind is driving into your face, right? Or into the inlet of the engine, right? And then we go through just component by component, and we got to know the job of each component. So the diffuser is turning kinetic energy into enthalpy. The compressor is putting mechanical power in to increase the enthalpy of the fluid. The combustor is increasing the enthalpy of the fluid by adding heat. Then the turbine is taking enthalpy out of the fluid to create mechanical power. But the turbine in this case, different than all the other heat engines that we've talked about, it's trying to produce as little power as possible. So it's only going to produce enough power to run the compressor. So the back work ratio in the Brayton cycle in the middle is only 1. And that's because we want to leave as much enthalpy as we can in the fluid as it goes into the nozzle, because the nozzle is going to take enthalpy and turn it into kinetic energy. And our whole goal of running these kind of cycles is to maximize the kinetic energy that comes out of the nozzle in the back, right? So it's that velocity that we're interested in. This means kinetic energy is going to be important, at least in 2 states in this cycle, right? At the inlet of the diffuser and the outlet of the nozzle, the 2 states that touch the air, also the 2 states that do not touch the Brayton cycle in the middle, right? We got to watch our units when we're talking about kinetic energy. And then we got what's going on in the middle here. This is a Brayton cycle, but it's a special Brayton cycle because the back work ratio is 1. So the power produced by the turbine is equal in magnitude but opposite in sign for the compressor. Another way to think about this is that the net work of the cycle, the mechanical work, W dot, that we calculate, is 0, right? So the turbine power is equal to the compressor power, but the signs are opposite. If we're dealing with metric, and we can make the assumptions that we usually make, then these are the equations we would expect to get, right? So for the diffuser, the new ones here are the diffuser and the nozzle, right? So here at the inlet, we have enthalpy and kinetic energy. We're turning that all into enthalpy in the diffuser. At the nozzle, I haven't separated by inlet and outlet, but really it's at the outlet you have enthalpy and kinetic energy, hopefully as much kinetic energy as you can. And the kinetic energy that you get, you'll find as the difference in the enthalpies between the inlet, which is state 4, and the outlet, which is state 5. Inside the Brayton cycle, power terms are still going to be m dot times h in minus h out. Heat transfer terms are still going to be m dot times h out minus h in. Again, provided we can make those same assumptions that we usually make. Now, this is for metric. It's a little trickier when it's imperial units, right? Because here we have to take those kinetic energy terms, and we don't just have to worry about the units. First, we have to get the quantity right. It has to be energy per unit mass, and it's not energy per unit mass until we divide by GC, right? And after we do that, then it's probably going to be something like foot-pounds per pound mass, and we probably are going to have to divide by 778 to get to BTUs. Right? And again, on this chart, I've kind of left this thing, right, to tell me that the back work ratio is 1. Right? So since it's an open book exam, I think I have a page like this for all of the different cycles. You know, print those pages out and have them in front of you, right? So that when you, oh, it's that cycle, these are the equations I expect. Now, you don't just want to write these equations down. You want to show me how you get to these equations. But sometimes when you're, you know, walking through a maze, it's nice to know where the exit is, right? So, you know, it's nice to know what the final equation looks like, because that'll help tell you what assumptions you want to make. Okay, so now without further ado, we're going to do a turbojet example. Right, so here, this is our turbojet problem, right? We're asked to first fix all the states, then find Q in, and then find V out. But because I don't like to fix all the states first, I'm going to do 2, then I'm going to do 3, then I'm going to go back and fix all the states. So I'm going to, you know, take my own medicine here, try to get the symbolic solutions first, because then I'm demonstrating that I know what I'm doing, and then I'll go through and fix the states. So here, I couldn't find the document where this problem is. So instead, I'm just going to use a blank document over here. Right? So here's our turbojet. Right? I'll go to the pens over here. Right? So we come in. Right? We go into a diffuser. I think we draw a diffuser or something like this. Then out of the diffuser into a compressor. Out of the compressor into the combustor. So this is diffuser, compressor, combustor. Then a turbine. And then here, a nozzle. So this we call state A, 1, 2, 3, 4, and then state 5 is the exit. If I was going to draw a TS diagram here, right, which is the kind of thing you could ask on a question. Another kind of thing you might see on a problem is something like, maybe it asks, or maybe, in a multiple choice question, maybe it gives you a picture of a TS diagram and asks you what the cycle is, and then you got to find it. Or maybe it gives you a picture of the cycle, and then, A, B, C, and D are different TS diagrams, and you get to pick which is the right TS diagram for that cycle. Right? So here, we can think of, when we're drawing these things, we can think of the diffuser as being like a compressor when we draw a TS diagram. And then we can think of the nozzle as being like a turbine. Right? So here's my state A. Right? This is at some low pressure. Now, I'm going to assume that the diffuser is isentropic. Right? So now I'm going to go to state 1. Right? This is at some other pressure. Then I'm going to, here, this would be the ideal diffuser, 2S, right? Up to some high pressure over here. But the real compressor is going to go over here to state 2. Then we're going to add heat up here to state 3. Then if we had some ideal turbine, we'd go here to 4S. But a real turbine is going to go down here to state 4. And then we'll still assume that the nozzle is isentropic down to state 5. Right, so here, right, if I wanted to draw this with the stuff on it, right, this is the power coming in, the power coming out. We have heat coming in here. Now, I'm going to use a different color. This is kinetic energy coming into the system and kinetic energy going out of the system. Right? But if I'm drawing these lines for the diffuser, and the diffuser looks like a compressor, it's on the same side of the cycle as the compressor, and the nozzle looks like the same thing that I would do for drawing a turbine. Right? And the other thing I'm going to do is remind myself up here, right? Because this is the thing people often get wrong. I'm going to say back work ratio is equal to 1. Right? And another way that I can do that is I'm going to draw a constant pressure line here and a different constant pressure line over here. So this pressure at 1 and pressure at 4 will not be the same, which is different than a normal Brayton cycle. Part B was find an expression for Q dot. Right? So here we're going to do the first law analysis on the combustor. This is where heat comes in. We've got dE by dt is equal to Q dot minus W dot plus the sum of M dot in, H in plus V in squared over 2. This was a metric problem, I believe. If we go back to our turbojet example. Right, so here's my problem. It's in metric, so that's good, right? I can, I don't have to do the GC over here, plus GZ in minus the sum of M dot out, H out plus V out squared over 2 plus GZ out. My assumptions here are going to be, right? That we're at steady state. We're not adiabatic because this is the thing we want to find, right? But we are passive. One inlet, one outlet, no kinetic energy change, no potential energy change. So we get the equation here that we expect, Q dot in is equal to m dot times H out minus H in, which is equal to m dot, the state at the outlet is H3 minus H2. If I was doing constant specific heat, then this would change to m dot Cp T3 minus T2. We'll see what our time looks like when we start fixing states. Definitely in the videos that I've made, I believe that the thermal short plus the long version, I show you conceptually, and I think even numerically, how to fix the state with both constant and variable specific heat. Today in lecture, maybe we'll just pick one, but I'll let you guys decide which way we do it. Part C, I think was what's the velocity at state 5? So if we're trying to find the velocity at state 5, if you don't know what to do, it's thermodynamics. So do the first law, right? You got to do the first law and touch state 5. So how about we do the nozzle, right? So for the nozzle here, right, this is going to be for the nozzle. This is dE by dt is equal to Q dot minus W dot plus the sum of m dot in H in plus V in squared over 2 plus GZ in minus the sum of m dot out H out plus V out squared over 2 plus GZ in. The thing that I'm trying to find here is V out squared over 2, right? So that's a kinetic energy term, obviously related to the velocity at the outlet. We're going to assume that the nozzle is at steady state, that it's adiabatic, that it's passive, one inlet, one outlet. We're going to neglect kinetic energy changes, and we're also going to assume that V4 is equal to 0. The way that I remember this is that the kinetic energy is only important at the inlet and the outlet. That it doesn't matter in the middle, right? So any state that touches the Brayton cycle, the kinetic energy doesn't matter. All right, so now here, if I do this, this is going to be 0 is equal to, there's only one mass flow rate, right? Because it's, so I could convince myself of this, right? So dm by dt is equal to the sum of m dot in plus the sum of m dot out. But because we're at steady state with one inlet and one outlet, m dot in is equal to m dot out. I'm just going to call that m dot. Right, so I have a mass flow rate. At the inlet, I've got H4. At the outlet, I've got H5. And I've got V5 squared over 2. I'm going to divide both sides by the mass flow rate so that m dot goes away. And then from here, I'm going to see that if I can move this, V5 squared over 2 is equal to H4 minus H5. But if I think about the units here, right, because anytime the kinetic energy term sticks around, right, the hair on my back of my neck is standing up, right, because this is going to be in kilojoules per kilogram. Here, right now, this is meters squared per second squared, right, which is meters times meters per second squared. Meters per second squared is an acceleration. If you get a unit like this and you get lost, remember that Newton was a pretty smart person, right? So Newton told us that force is equal to mass times acceleration, which must mean that acceleration is equal to force over mass, right? So this is also equal to meters times newtons over kilograms, right? Newton meters per kilogram, that's only joules per kilogram. So here, I've got to multiply this side of my equation by 1 over 1,000. And if you're curious where that comes from, my spacing here is not great. So I'm going to do this over here, right? So right now I have joules per kilogram. So I know that there are 1,000 joules. I put that on the bottom because I want to cancel out the joules for every 1 kilogram. So here the joules cancel out and I will get kilojoules per kilogram. So because my velocity was in meters per second, right, then I can divide by 1,000. But if my velocity was in, this will give me a velocity in meters per second. If I wanted it in kilometers an hour, then I'd have to do a different unit conversion. But this will give me a velocity in meters per second, right? Now, again, if I was going to do a constant specific heat problem, right, then this delta H would become Cp times T4 minus T5. So the good news, right, is that I've got equations, right? I can find this heat transfer rate if I know the mass flow rate, which is given. The mass flow rate is 25 kilograms per 25 kilograms per second. So I can find Q dot, right? So over here, I guess the things that I know is M dot. Here, if I look over here at this state table, I'll take a snip of this and bring it in. I don't know very much, right? I know the velocity at the inlet. I know some temperatures here and a couple of pressures, but that's it, right? Not very much, right? So here, I'm going to copy this and bring it into here. We'll see what Word does. Word never seems to... It's not Word's fault, right? It's not the program, it's the user, right? Okay, so here, right? Okay. So now I got to go through and fix stuff. In particular, the stuff that I need to get answers, right? If I'm going to do a variable specific heat analysis, then the things that I need are H2 and H3. So things I definitely need: H2 and H3. And here I need H4 and H5. Right? And then if I was doing just a constant specific heat analysis, I wouldn't care about the H's. I would just need the temperatures. Right? So I would need these temperatures. So we've done as much of the problem as we can without making the decision between constant or variable specific heat. So I'll try to go through the whole thing in one of these methods. You guys can choose. And then if there's time at the end, I'll go through the other method. But you can see in my thermal shorts, I think I go through it both ways. Does anybody have a preference for constant or variable specific heat?
Could you do variable?
Sure. I think that we've done some constant stuff in the past. So we will go through it. I will give you the numbers. I won't show you the interpolation because I think I have the numbers here, but I will definitely show you the process. Right? So with a turbojet, there's sort of two parts, right? So basically with air, anytime you're dealing with air, your starting places are going to be the places where you have temperatures, right? So I'm going to start at state A because that's the place that I have the most information. But if I get stuck somewhere, I'm going to move to state 3 because I also know the temperature there. Okay? The other thing that I need to know is I need to know, because it's air, I have to identify the isentropic processes. So we're going to say that the diffuser is isentropic and the nozzle are isentropic. I can't see. Let's see if it says here. It didn't tell us turbine or compressor efficiencies. So for right now, I'm going to assume that the compressor and the turbine are also isentropic. But if they were not, if they were real and not isentropic, then we would still have to find the isentropic state. It's just that then we would have to use the isentropic efficiency to find the real state, right? So I won't go through that unless someone specifically asks. Sebastian, looks like you have a question.
Would you tell us if it was real or ideal
Yes.
on the exam?
So if you don't get an isentropic efficiency, or I don't ask you what the isentropic efficiency is, then you can assume that it's ideal. I will try to be as explicit as I can. So there's two ways to ask isentropic type questions. I can give you the efficiency, make you find the ideal outlet, and then use the efficiency to find the real outlet. Or I can give you the real outlet, you can find the isentropic outlet, and then tell me what the efficiency is. Right? So either I'll give you the state information to find the real state, or I'll tell you what the isentropic efficiency is. So I think those are the permutations of how that type of problem can work. So the first state we're going to fix is state A. Right? So state A, this is good because we have the temperature. Having the temperature is great because now I can go on table A22, right? And I can use the temperature to find HA. And then anytime you're working with ideal gases, if it's an open system, you're going to want to find PR. And if it's a closed system, you're going to want to find VR. So because this is an open system, I'm going to go and I'm going to find PRA. Right, so here, when I did the numbers, it looks like I didn't actually solve this thing. HA, table lookup at, it looks like it's 230.02. Kilojoules per kilogram. And PRA is, I don't know if I have it here, but you could look it up on the table, right? So, but you would, so we would look this up. Okay, now what's going to happen is we're going to try to find state 1. So as we go in between state 1 and state A and state 1, this goes through the diffuser, right? So this means we're going to turn this kinetic energy into enthalpy over here. The only way I can figure out how to do that is to use the first law, right? dE by dt is equal to Q dot minus W dot plus the sum of M dot in, H in plus V in squared over. We know that this is 2000. We've already talked about how to do the units there, right? Because this is in meters per second, plus GZ in, minus the sum of M dot out, H out plus V out squared over 2000, plus GZ out. We're going to neglect kinetic energy changes. We're going to say it's one inlet, one outlet. It's the diffuser, right? So it's the inlet kinetic energy that matters, right? That's the one that doesn't touch the system. We're going to neglect, or we're going to say it's at steady state, and we're going to say it's adiabatic and that it's passive. Right? Now I'm going to divide both sides by M dot, right? So that M dot will drop out. And we will get that 0 is equal to H1, or HA, I'm sorry, plus VA squared over 2000 plus, oh, sorry, minus, because this now goes into this other bracket, minus H1, which is H out. At this point, we know HA because we found that from the table. We know VA, that's given. The thing we don't know is H1. So I use this equation to find that H1 is equal to 254.02. Now remember, table 822, it's got a temperature, right? It's got probably U, H, S superscript 0, PR, and VR. Might not be the right order, right? But now here on table 822, for state 1, we know H. I'm going to use this to interpolate and find the temperature, and also to interpolate and find PR. Right? So really, actually, I'm not even going to find the temperature. It's not ever in my equations. So let's pretend it's a test situation, although I'm talking throughout the whole thing. So maybe not, right? But I'm not going to find temperature because it's just going to take time. But I am going to interpolate to find PR1. PR1 is approximately 0.776. Now, you got to look at how much time you have left when you're interpolating, right? This will now be the third exam. So, you might have to interpolate, but I'm less interested in you demonstrating your ability to interpolate. So if it's around halfway, just pick a number around halfway. If it's around a quarter of the way, just pick a number of quarter of the way. Don't spend a lot of time doing the arithmetic for interpolation. So we have the H and P, but we would like to actually get the pressure here as well, right? So this process, in addition to being able to use the first law, which I can also use, this process is one of those processes where delta S is equal to 0. And when delta S is equal to 0, I always want you to do this equation. Well, let's see. We're trying to find P1. So that we'll do P1 over PA is equal to PR1 over PRA. Right? I can isolate and find that P1 is equal to 36.9 kilopascals. I will need this pressure because I'm going to move right from this diffuser into another isentropic process. So I'm going to have to use P1 again later. So now, as I've gone from 1 to 2, or now I've gone from A to 1, now I can go from state 1 to state 2. I don't think we know anything about state 2. Right? So actually, it must give us the compressor pressure ratio. I think we must end up knowing what the pressure is. Let's see as we do the analysis. Right? So here, right, what we're trying to do, right, is we're trying to find, maybe we would want the power from the compressor. Right? If we can say that it's steady state, one inlet, one outlet, neglect kinetic and potential energy, and what else do we have to do? Say that it's adiabatic, then we're going to get m dot times h in minus h out. Maybe we don't need this. Maybe we do, right? But maybe they tell us the power consumed by the compressor. So this would be what we'd get from the first law if we needed it, right? We could use, this is an isentropic process. Delta S is equal to 0. So because this is an isentropic process, we can also use P2 over P1 is equal to PR2 over PR1. So I believe in this problem, they would give us the compressor pressure ratio. So here, or maybe they would just give us P2. So here we would either have R or we would know P2. If I was being sneaky on an exam, I would just give you P2 because then you would have to come back here and find P1. If I just gave you R, you wouldn't necessarily need to know what P1 is. Right? But let's say that we know P2, so then we know PR and P1. What I really would like to know is PR2 right? So from this equation, I find that PR2 is equal to 8.536, right? This is a dimensionless quantity. Now I'm going to go to table A22 and find H2, and it's approximately equal to 505.1 kilojoules per kilogram. If I cared about it, T2 is approximately 502 Kelvin. But again, unless this was asked for in the problem, I don't really have to do it. Right? Now, here's the cool thing, right? So now we're, right, if we do, right, so we had our diffuser, which we did, right? Then we had our compressor, which we did, right? Now we're at the combustor, right? So as we go through, so we did A, 1, 2. Now we're going to go from state 2 to state 3. The best part about state 3 is they told us T3. Right? And we know that we're going to assume constant pressure Q dot in. Right? So that means that P3 is equal to P2. Okay, so what do? I know T3. So because I know T3, I go here to table A22. And from this, from T3, I get H3 and PR3. So when I looked up H3, it was 1,515.42. It's still going up because we're adding energy in the form of heat into the fluid, so its enthalpy keeps going up, and then we can get PR3 is equal to 450.5. This has no unit. At this point, I may have noticed that now, remember my equation for Q dot was m dot H out minus H in, so H3 minus H1. Or H2, I'm sorry. Now I know all of this stuff, so I can find that Q dot in is equal to 25,258 kilowatts. So now I answered part 2 already because I had the information. I could maybe go through and do that at the end, but we'll pause here just to realize that we've already done that. Now this next part is the part where people often make mistakes. Because the next thing that we do, right, is we go through our turbine. Right? And then over here, this is our nozzle. So now we're going to do the turbine. For Brayton's or for turbojet engines, what's the back work ratio? It's 1, right? What's the net power? 0, right? So here we know that if the back work ratio equals 1, then that also means that W dot net is equal to 0, right? That's going to be the turbine power plus the compressor power, but the compressor power is negative. If we make all those assumptions that we already talked about, this is going to be 0 is equal to m dot through the turbine, H at the inlet of the turbine, which is H3 minus H4, plus m dot at the compressor, H1 minus H2 is equal to 0. Both of these mass flow rates are the same, right? So I can divide both sides by m dot and cancel that out. The thing that I'm trying to solve for here is H4. So here I can see that H4 is going to be H3 plus H1 minus H2. And I know all of these things already. So this is going to be 264.3 kilojoules per kilogram. Right, so now we have H4. When we have H4, that means we can go to table A22 and I can interpolate to find PR is equal to 228.9. No units. But now the question becomes, well, what's the pressure at the outlet of the turbine? If this was a normal Brayton cycle, the pressure at the outlet of the turbine is the same as the pressure to the inlet of the compressor because both of those things touch the air. But that's not true in a turbojet. So it's got to be something different, right? So instead, what we will do is we'll find, because this is delta S is equal to 0 across the turbine, at least the ideal version of the turbine, which is all we have here. So this is going to be P4 over P3 is going to be equal to PR4 over PR3. And from here, I can find P4 is equal to 206.2 kilopascals. I don't need it, but if I wanted the temperature at state 4, it's 1,188.5 Kelvin. Right? Unless it asks me what the temperature is, I wouldn't spend time interpolating to find that on a test. So now we're almost done, right? We fixed all the states, except we need to go through the nozzle. So how do we do this, right? We already did a first law analysis on the nozzle up here, right, to do our symbolic solution. And we found that V5 squared over 2,000 is equal to H4 minus H5. So we know V5 squared over 2,000 is equal to H4 minus H5. This is the thing. Remember, the problem is asking for this. You're basically always going to have to find the outlet velocity on a turbojet. We know H4, but we don't yet know H5. So how do we find H5? Anytime we're doing a cycle where the fluid is an ideal gas, we remember that delta S is equal to 0, which lets us use the right equations here that here we're trying to find. So we got P5 over P4 is equal to PR5 over PR4. Here, P5 is equal to PA. Sometimes it'll tell me that, sometimes it won't. But if we remember, right, here's the diffuser, then there's some stuff up here. Here's the nozzle, right? This is state 5, this is state A. The states that touch the atmosphere are always the same in terms of pressure, right? So the temperatures are different, right? This temperature is going to be a lot hotter than the inlet temperature, but the pressures are the same, right? So we know this. We found PR4, so we use this expression to find PR5. PR5 is equal to 28.9. Then I go to table A22 and I interpolate to find H5. I see that H5 is 714.0 kilojoules per kilogram. That's great, right? Because here now I have a value and I can solve for the velocity at state 5. I get that V5 is equal to 1,049.1 meters per second, right? This is our moving frame of reference. So if you're the person standing on the wing, it looks to you like the air is streaming out the back of the jet at 1,049.1 meters per second, right? But if you're somebody standing on the ground, right? So to get V5 in the stationary frame of reference, this would be V5 moving frame of reference minus the velocity of the jet, which for us in this case, because we're not going to talk about headwinds and tailwinds and stuff, this is the same as VA, right? So this is going to be 829.1 meters per second. And that is how we go through and do a turbojet problem. So the good news with the turbojets is that there's not a lot of extra complexity we can add. We can add something like an afterburner where you have another heat addition process before you go into the nozzle. So then you'd have another heat addition process. Probably you'd be given the temperature at the inlet to the nozzle. But other than that, they're usually kind of the same, right? Now, you could get different permutations of the known information that you have, but the key points about this turbojet problem to do it correctly are you have to get your units right with kinetic energy. If I ask you this problem and it's imperial units, it will be harder than if it's metric units, right? Because then you got to divide by GC, then you got to divide by 778 probably, right? The other thing that people often mess up here is that that they forget that the backwork ratio is 1. So people will often set the pressure at the exit of the turbine equal to the pressure at the inlet of the compressor, and that will that'll mean that their turbine is consuming or is producing a lot more power than it quote unquote should, which means you'll get a lot less velocity coming out. So if you get a velocity that you feel like is really low coming out of your turbine, then that's probably the problem. If you get a velocity that's like faster than the speed of light, it's probably because you messed up your units, right? Or if you get a velocity that's really, really tiny, like a factor of 100 too small or something, then it's probably that you messed up your units, right? So usually if you get a really enormous number or a really small number, it's probably a unit conversion issue. And in this problem, it's probably because of that kinetic energy term. So that's all I have. If you go through and you look at the video, certainly in the long version of the video, in the thermal lecture series, and I think also in the thermo short, I do kind of a side-by-side for each state showing how to fix it with a variable specific heat, which we did here, but then also a constant specific heat. It's essentially the same problem. If this was a constant specific heat problem, basically every time we used this equation, instead we would have used T over T is equal to P over P to the K minus 1 over K, right? You got to check out the equation sheet. I never remember if this was P5 over P4. I never remember if this is P4 over P5 or also P5 or P5 over P4. So check this out on the equation sheet, but it ends up being kind of the same. The nice thing about constant specific heat is that you don't have to do the interpolation. If this was a variable specific heat problem on an exam, as you can see here, there's a lot of, and then I went to table 822 and I did a bunch of interpolation. So if this was a constant specific heat problem, you'd probably expect to maybe have to fix some more states because all you need for constant specific heats are the temperatures and pressures. So you don't have to do any interpolation. For variable specific heat problem, probably your state table would be a little bit more filled in. Does anybody have any questions? Because that's all that I had to present to you today.
Can I ask a question about like a different question?
Sure.
Yeah, a different. So if we're talking about regenerative process, I know that the regen like part does not have Q like Q in or W out. Like if we were talking about I think it was a Brayton cycle with the regenerative process plus intercooling and reheat.
Yep.
We're just talking about solely the regen part.
Mm-hmm.
What would be the equation for that regen part? It's not Q is equal to M times
Oh,
H.
this is a good question.
Out.
And I'll show you how I can trip you up. So first I'll do the normal version, right? So normally we would have our first law, dE by dt. I can't remember what the numbers are, right? But let's just call this A and B and C and D, right? And this part is going this way, and this part is going this way, right? So dE by dt is equal to Q dot minus W dot plus the sum of M dot in, H in, plus V in squared over 2 plus GZ in, minus the sum of M dot out, H out plus V out squared over 2 plus GZ out. Normally, the assumptions that we'll make here, right, are that it's steady state, one inlet, one outlet. It's got no fan blade, so it's passive. We'll neglect kinetic and potential energy because there's not diffusers or nozzles, right? And then we'll normally say that it's adiabatic, right? What that means is that all the heat from the big thing, from the hot side, goes into the cold side, that none of it escapes from the atmosphere. If this is what we get, then we get 0 is equal to the sum of M dot in, H in, minus the sum of M dot out, H out. This would be, if this is a Brayton cycle, these, the ones we've talked about, the mass flow rates are all the same, right? So the going in states, this would be HA minus HB plus HC minus HD, right? And then typically, maybe you'd use this, right? The other equation you might get here would be the regenerator efficiency, right? Which would be the heat that's actually transferred divided by maximum heat transferred, right? This is talking about the heat that goes from the hot to the cold, right? So here we're going to look at the cold side, the actual transfer, right? This is going to be H out minus H in if we did the first law and kept Q. So this would be HB minus HA divided by the maximum temperature that we could get is HC. This is the hottest port on our thing. So this would be HC minus HA, right? And this would be our regenerator efficiency. So sometimes you have to use both of these equations. So you could use this equation potentially to find, maybe you use this equation to find HB, right? And then that you could put in here to find HB, and this would maybe let you find the exhaust temperature. That's often a question, right? This goes to the exhaust, right? Because when you do this, maybe you'll find that you'll know HA and HC, but you won't know HB and HD. So then you use the regenerator efficiency to find HB. You plug that in here, and then you can find HD. I could throw this, pardon me?
No, sorry, I was going to say, yeah, thank you. You keep going out.
So I could mess you up a little bit, right? Or let me rephrase that. I could give you an opportunity to better demonstrate your understanding of thermodynamics if I tell you maybe there's 10 kilowatts of heat loss that comes out of this thing. Then this is not adiabatic, right? Because this is only adiabatic if all the heat, like if none of this heat transfer goes across my control volume. But if there's some heat loss from this system, right, then you'd put a number in here, and your Q dot term would be, it would have the same sign as the H in terms, right? So this would be plus Q dot in here, right? And this would be plus Q dot. So then you'd get a slightly different answer for HD, right? I think I got the sign of this right, but that's why I think it's better to understand, like this is a good example of why it's better to understand the process of how to get to this equation, right, than to just memorize this equation. Because if you memorize this equation, yeah, it'll work unless I make you relax one of these assumptions, right? And if you're going from the first law, then you'll be able to demonstrate to me, like, I don't care what assumptions you make me make, right? Or you make me relax, because I just get the equation from the first law. So it doesn't matter what assumptions you get, right? So this can be super hard if you just memorize this equation, right? But I think it's easier, right, if you go from the first law, even though it takes a little bit more time to write that equation down. Does that make sense?
Yes, thank you.
You're welcome. Any other questions? All right. Thanks, guys. I got to get used to, limiting myself to 50 minutes here, because usually there'd be another professor barging in the room. And so I'm looking forward to the fall when we can, be in real life again.